Hello, hello. Welcome to Plasma Implementers Call 21. Incredible. Well, we've got a number of people, on the call, and a few new faces. In fact, why don't we start off with Andy? Introduce yourself. Who you are, where you're from.
So hi, so I'm Andy. I'm based in Tokyo, and I'm working for Omisego now. So yeah, before that I worked for Plasma Cash for Omisego as well. And recently, our company is trying to roll out the predicate design, following up the Plasma group, and also we're trying to roll out our DAX on top of that. Yeah.
Nice. And there's another new person on the call, Will. I'm curious. Say hi.
Hey, how's it going? So I'm Will. I'm from Chicago. I work at Consensus currently, but I'm going to be working with Carl and Ben and the team on implementing some Plasma stuff.
Woo! Yeah, we've got this spec which a lot of people have seen, and getting tons of implementations done. So this has actually been a pretty action-packed week for us, but I don't know what's been up with all of y'all organizations. Why don't we all give like little status updates on what we've been working on, what we've been thinking about. There's been a lot of discussion in the plasma.build forum, which we can get into. But I think that would be a fun way to start it off.
Okay, should we go ahead?
Sure, go for it.
Have an introduction?
Yeah.
So hi, my name is Yuriko. I'm from Crypto Economics Lab with Shuhei right there. He's also in the call. And we've been recently researching how to standardize predicates. And our most recent post on plasma.build is blending predicate. And that's what we've been talking about since scaling Ethereum.
Nice.
Yeah. So, yeah. Shuhei, do you want to add something?
No, there are no big updates. So, okay.
Yeah, that's pretty much it. Yeah.
Shashank, why don't you give us a little update?
Okay, sure. Yeah. So our focus has largely been on two aspects of Plasma. One is around the data unavailability, because we take a slightly different tack, right, with the account-based Plasma. And our first model really focuses on essentially sort of a token-based voting, right, to halt. And that is something that we've been wanting to improve on and come up with something more generic. And so one of the things that has kept us thinking, and we are certainly just now slowly embarking on it, is to see if we can use a consensus mechanism to establish whether one should, keep moving forward or sort of do a chain halt. And one of those, within those sort of subsets, has been Tendermint. So we're looking at if we can somehow use Tendermint potentially as a consensus mechanism within the Plasma chain. It's a little bit of a stretch. It's very experimental at the moment. We don't know whether that even makes sense, because the whole sort of validation model and consensus model has its own complications and overhead. And that's something that we've been experimenting with. So that's one piece. The main chain is live, and there is a sort of a spot exchange that is working on it. So so far we haven't seen any issues, but it's also been new. There hasn't been that amount of traffic either. So, sometimes these come up as traffic picks up. Our product, which is what inspired us to get into Plasma in the first place, was largely around leveraged and derivative products. And that has some additional complications beyond, payments and just standard exchanges of maintaining margins and, taking off what has been commonly called insurance funds. And modeling that in the world of Plasma has been interesting. So we've been looking at, do we need to add more constructs to it? We don't want to corrupt it. We want to keep Plasma more sort of, broad-based and just do a lot of these in the app itself. But in some sense, what we call balance commitments in the main Plasma world, I think doing that to open positions has been a little bit of an interesting modeling exercise. So that's also underway. That's something that I've been working on. So that's, I think, broadly the bigger pieces. And beyond that, the last but not the least, I think I'm very interested from learning from everyone is what is the right validation window, right? So what is the right amount of time that assures in some sense that you've had enough validation, right? And I've seen that various models have various timelines. In fact, the more people I speak to, it seems like the timeline is only varied. Some people are comfortable with 24 hours, some people think a whole week, some people think a few minutes. And I don't know if there's a hard science behind it. I actually do not know. So I would love to hear if you all had your own experience around it. So that's it. That's for an update and a question as well. Thank you.
Cool. Yeah, I think we'll totally get to that question. I definitely have things to say about it. But yeah. Ben, do you want to give a status update for Plasma Group?
Yeah, sure. So Plasma Group, last week we were busy at an awesome conference, which we were lucky to see some of you guys at, Scaling Ethereum. So we've been doing a few cool research things came out of that. One of the more interesting ones, which we posted about on Plasma Build, is this notion of mass exits via the rollup mechanism. So hopefully we'll get a chance to talk about that more in depth. But it seems to us that that Plasma is a really good fit for this, and we can probably do a very high number of like exits per second on the Ethereum main chain at a much more reasonable cost than we would have expected. So that's pretty cool, and that's one of the main things that we've been looking at, figuring that out. And also another thing that we went over at Scaling Ethereum was taking a look at Dan Robinson's Rainbow Network paper, which Shashank, to speak to your derivatives thing, is like a synthetics leverage-based agreement that's done within state channels. So it's been interesting to look at what Dan's been working on there, and especially since you can put channels on top of Plasma, it seems like a cool fit. So some fun research there, especially the mass exit stuff. Excited to talk about it more later on.
Very cool.
Cool. Matic.
So yeah, we are working on predicates for the last couple of weeks, specifically ERC20 and 721. And right now on our roadmap is a predicate for atomic swaps. And yeah, we are thinking about predicate interoperability while we are on it.
Very cool.
Cool. Well, I guess we've already started covering a little bit, but the output from Scaling Ethereum was a super duper cool conference, and we discussed a lot about both synthetics as well as Rollup Plasma, although Rollup Plasma is my favorite little output. Maybe we can talk a little. Shuhei, do you want to talk about the lending predicate that you came up with?
Okay, in short.
Sure. Yeah.
Lending protocol. Okay, so just a moment. Okay, so let me explain lending protocol in short. So, okay, most important thing in lending protocol is there are two general features of offline swap, and timeout feature is most interesting point. Lending predicate has two steps. The first step, lender make the kind of the collateral state and make swap to make swap for loan token to borrow money. In second, just a moment. So collateralizer should sorry, just a moment. There's two steps in lending. First, the collateralizer swap collateral for a loan token to borrow money from the lender. The collateral was wrapped by collateral state. Second, collateralizer can swap repayment for collateral. It is like offline swap. The collateralizer can swap without render's signature. And collateralizer can send collateral to other users as long as recipients verify the swap is valid or not. So it means the extra history to verify.
Mm-hmm.
Oh, I think that's our.
Yeah, I think so.
And swap. So it is basic step of the rendering predicate.
Super cool. I was super excited to see this, Shuhei. I think it makes a lot of sense. I think that you mentioned that Dharma protocol was where you got a lot of this from. Yeah. This seems like a great fit for Plasma. This is one of the things that I know at Plasma Group we've been talking about a lot, is that the difficulty of writing predicates is that you still need to have a strong sense of ownership, right? Like you still need to know that one particular person is like responsible for maintaining this money. And so loans are like a great example of this, because there's, some lender and some collateralizer, and they are both interested in keeping, like the collateral money locked up and receiving the loan money. So it's super cool to see that, because I think it totally works. It's awesome.
Okay, just to add on to his explanation, he wanted to stretch that this is just one of the examples of predicates. So it's not really critical to discuss with everyone here, but this predicate has two general features, standardized features, offline swap and timeout. So it can be used with other predicates as well. So that's why he wanted to bring up this example in front of everyone. So
yeah, thank you.
Yeah.
Oh, I see.
Yeah.
So the idea is you can basically make this generic so that like it doesn't have to act as an ownership predicate at the end. It might act as something else or be dependent on different conditions. Yeah.
Right.
Cool.
Yeah. Thanks for letting us introduce this idea.
Yeah, for sure.
It's great.
Yeah.
One of the interesting things I think we've been finding in like predicate, sort of as we're going about predicate design recently, is that you're definitely right that like the best way that you can do it is make a generic one, some sort of standard one that doesn't actually do anything, and then add the stuff that you want to do on top. I know that like that has been like there are many cases, for example, we have this notion of limbo exits as a predicate, and like the idea is that the ownership predicate and like say a multi-sig predicate should really be the same, most of the same code. There's really only one line that needs to change where you need to check two signatures. So that kind of like abstraction is totally like awesome, and like definitely going to pay dividends down the line.
So I'm also excited. I'm excited to talk about the Rollup Plasma, because it is a very fun thing, move forward. So unless anyone has any objections, I'm going to dive in. So I'm going to share my screen real quick. Just show the post, which is very bare bones and doesn't really give very much description about like what this thing is. But this was definitely the most surprising, unexpected output from scaling Ethereum that just kind of came out of nowhere a little bit. So basically the idea is
it came from Barry.
Exactly. Yeah, we're huge fans of these Rollup designs.
We have Vaibhav with us. I can call him. So he's on Rollup with Barry Whitehead. So yeah, you can start, but he will be here. So he's working on Rollup mostly with Barry Whitehead. So maybe he can see also this one.
Yeah. So full disclosure, Barry. Yeah. Barry, anyway, Barry wants okay, we need to talk about the naming with Barry, but okay, let's dive into the actual thing. So Rollup for mass exit. So basically what we're doing is we're taking a lot of the techniques that are used in these rollup chains, which is, putting all of the information in call data, and then Merkleizing that information, and then only storing the Merkle root of what you put in call data, which is a very common technique. Basically, the problem in Ethereum is, it's very expensive to store in the state, but it's a lot less expensive to store through the call data. And the call data allows you to, make sure that the information, at least at one point, was made available. So the reason for this disparity in between state and call data is that state is required to be held on to by the nodes forever, and the call data can technically be pruned if so chose, if the node would like to, because it's just part of the history. It's not part of the state. And so what we did was we're just saying, oh, there's ZK Rollup was the first introduction to Rollup, right? And it was introduced by Vitalik in this post, and that essentially used this call data plus a zero knowledge proof to verify that the call data state transitions, call data representing the state, and verifying that the state transition from one state to another was valid. However, we realized that we can actually just use Plasma for the state transition verification, because that is kind of what Plasma is for. And so these are some very preliminary. We haven't implemented this yet, full disclosure. We realized this is possible, a week ago. But we do have some relatively reasonable gas calculations that will can estimate the actual transactions or exits per second, right? And so basically what we realized is we can kind of compress a lot of this information, get our exit messages down to less than 100 bytes, and then we're just here we're calculating the cost of the S store. That's for the Merkle root. So the general technique is you put all of the information in the call data, you Merkleize that, and store the Merkle root. So the actual gas cost comes from the call data, which is quite expensive, relatively speaking. The one S store for the Merkle root, and the Merkleization and hashing of all the information. And so this is what kind of went into these calculations. And so we have, this is the gas cost for SHA-3 on some amount of bytes. This is total gas in a block. The gas per exit, and this includes the gas per byte of each one of these transactions. So we're just like multiplying how much it costs per byte, and then we're multiplying by the exit bytes. And we, basically run through a bunch of stuff, and we end up getting something like 1,800 exits in a single block for these parameters, right? Well, we can see how this exit bytes, we may be able to express this with less data, maybe more data, who knows? But this is, up in the ballpark, and it seems reasonable in terms of just like being in line with what the kind of roll-up scalability folks, say and calculate. So yeah, that gives us something like 128 exits per second, which is kind of crazy. Because that, like a lot of our problems have been this kind of, mass exit vulnerability and blah, blah, blah. Like a lot of these things are lessened. There's still problems because in fact, if we just used rollup chains, then we'd be capping out at, maybe 128, maybe 128 plus some safety factor. There's an interesting thing here, which talks about how if you do this in an optimistic way, you can actually get past the 128 transactions per second that a normal rollup chain would be, but I won't get quite into that unless y'all really want. But the basic idea is that the applications that weren't really possible on Plasma because the ownership was not very clear, we can do on a rollup chain, on a Plasma rollup chain, pretty easily, because we're putting all the information on chain, and we just realized that we can express that information in a very compact way. So I said a lot of things. Are there any questions? Oh, an important note before everyone, asks all your questions. The Stark Dex just came out recently, just as a kind of comparison. The Stark Dex came out pretty recently, and it's using roll-up-ish techniques, not exact, it's actually, I don't think, putting all the data on chain. However, their numbers are looking like it's either 95 transactions per second, or it's significantly lower, more like 15 transactions per second. I know that they're only testing with 15 transactions per second, so that's how much they're like, pumping into their decks at this time. But they can, I'm pretty sure, reach something like 90, 95 transactions per second in very optimistic cases. Like it may even be quite difficult to reach those numbers. But I was just trying to come up with some ballpark estimation. So as one might imagine, this is actually significantly cheaper than any of these ZK roll-up techniques. And the reason is because we don't need to do any snark verification on chain. And the trade-off is that we now, instead of having instant exits, which you get from these ZK proof roll-up chains, you have to wait the exit period. But you get more scalability. So.
Yeah. Carl, a couple of small questions, just curious. So this seems very, very exciting, the whole roll-up development. What is the payload size? I may have missed that, but did you guys do any calculations there?
When you say the payload size, are you talking about the call data? How much send into it?
Right. Because in some of the other techniques which also involved, zero knowledge proofs at large and roll-ups, and I remember speaking with, Alex and a few others, I think that was one of the limiting factors in terms of the payload size as well. Right, and they had to work around it. So what do we learn here in terms of the payload size?
Yes, great question. So we are actually limited in the exact same way that we are limited that they are limited in their payload size, right? So call data, you have a limited amount of call data. These exits per second are all calculated using the entire block for exits, right? The entire Ethereum block. So this is how we get, this is like the max amount of exits we can get in 1 second. So the call data is still a limiting factor. There is one nice thing about Rollup Plasma rather than a kind of ZK rollup, and that is that we don't have to put this payload onto the chain every single step of your kind of rollup chain. So the difference is we can actually do this kind of optimistic state transition payload pumping. Oh man, that was a weird way to say this, but we can do this optimistically. And what does that? Why is that the case? Well, you can use, if you use rollups with ZK rollups, one of the properties that's really nice to maintain is this fact that you have instant exits. And you can enter instantly. So you can say, I want to leave the rollup chain and get sent out in the next block. In this kind of Plasma rollup, we can't do that because we have to play the exit game on this large state transition for these different blocks. And that means that we're imposing a 1 week delay, 1 week dispute period anyway. And so if we have this 1 week dispute period, what we can do is we can say, okay, not only are we going to play this 1 week dispute period, but we can also just say, whatever, let's not put the information on chain, and then we can allow for challenges to then initiate one of these kind of roll-up disputes. And so then you only are putting the information on chain in the case of a dispute. And that is actually something you can do with rollup. And in fact, Barry has constructions called rollup rollback, which kind of follow this design pattern. But this is like an especially tempting design pattern in Plasma because we already have this dispute period. And it does mean that we get more transactions per second by quite a significant degree. And that is kind of right here. You can calculate it yourself. Because it's all about halting the chain, actually, which is an interesting thing because, Shashank, you were talking about chain halts, which I think are great in this, especially in this construction.
Yeah, seems very exciting. Thanks for sharing. Where is more information on this? Because where can one read up or look up code, or where is stuff around Plasma Z rollups at the moment?
So right now there is very minimal information on this stuff. We are very likely going to like put together a kind of sample smart contract for this, just because it's like a good thing to know how to do. But y'all should implement it, and if you do have questions, definitely ask in the plasma.build forum, and I'll try to explain more. And feel free to implement something like this, because it's a really cool construction, and it really does, I think, satisfy a large class of applications that were not very possible on Plasma because of the weirdness of state and the limitations we believed we had with regards to dispute resolution on a mass scale.
Cool.
I have a question. Did you do the calculation based on the normal Markov tree?
Yes, normal Merkle tree.
Okay.
So, one thing to note there is that this does require a scheme for what we've called optimistic exits. So this does not work nearly as well if you have to do an inclusion proof of the exit up front. And so rather what you need to do is introduce a optimistic exit where you say, I claim that this thing was included in this block, and I claim that I'm exiting it. And you can play either a normal exit game on that, or you add a challenge type, which is challenge inclusion. And that is a claim that I claim that no, that thing was not actually included where you said it was. And basically, if you have that's like a very important thing. So the Merkle tree, you wouldn't do this for the sort of any other sort of the interval tree that we do, because the Merkle tree is just over all of the exits. And then another note here is that one of the ways that this efficiency comes about, it comes with a requirement that you must submit a bunch of exits in a batch, right? The way this works is you take a large number of exits, you put them in a batch, and the Plasma contract is you get a scalability because the Plasma contract only has to store the Merkle root of all of those batched exits. So it is complex from a user coordination standpoint, depending on what kind of things you're trying to batch.
So,
Okay.
so if I understand correctly, the exit data itself should have the block to indicate which block it's in, right?
Yep.
There's no way to challenge the inclusion. Okay, got it. Thanks.
Also, I was wondering, do you have any estimation on the number of constraints for this type of snark construction, so that we can get a estimate on the proving time and the cost of proof?
The greatest thing about this kind of construction is that it actually does not use zero knowledge proofs. So all it does is it uses the dispute resolution exit game that Plasma uses, and it does this over larger state transitions, and you post all the information on chain. And so where there was a ZK roll, a ZK snark, right? ZK rollup, this is kind of Plasma rollup. And so that kind of gets us away from having to think about zero knowledge proofs, because they're kind of the proving time and it's a lot of implementation stuff. But by the way, long term, I think that we will have snarks and starks all over Plasma, all over these things. But for the short term, it's much easier to build an exit game.
Here, everything looks good. So it has to something some catch here. Some limitations you think about it. What will be the limitations here?
Yeah, I would say there's a few limitations. definitely. It is possible that that this increases your timeout period by one time period, because basically in the event of well, it depends. We actually have to figure that out. I think that's probably the next bit of research to do. But in the worst case, I can see this increasing the timeout by one exit period because of data withholding around the challenge inclusion. So it's unclear, but it's possible that you actually are not so worried about that. The other complication, like I said before, is that this does require some cooperative thing. So like the way that this gets scalability is that instead of making 100 function calls that stores 100 exits on chain, you make one function call that processes 100 exits and stores just the Merkle root on chain. This is how you get the advantage. And so like for like Alice and Bob and Carol and Dave to do this, like there has to be some relayer, or they have to cooperate in some peer-to-peer way. Because if they're exiting, maybe the operator's hostile, so we can't assume that the operator is giving them, peering. But once you have, but once you can do that, you get this way faster sort of exits per second number. And in practice, it's also like these estimations are on filling up an entire block. So like this is literally one block with one transaction that contains, whatever, 1,000 or whatever it was exits, and it gets efficiency gains from that, because from those 1,000 exits, all it stores on chain is one hash. So that's very nice, but it's probably not realistic to be filling up whole Ethereum blocks. I'm not sure if anyone, if that can be done with a single transaction. I don't know if people do that.
Yeah.
But it's definitely like, could be problematic.
Yeah, and this is very much like mass exit territory, right? So you are like, I don't think that these rollup chains would be used as the kind of like daily driver for all of Plasma, right? This is more a technique for building applications that are not really feasible on a kind of a normal Plasma chain, but that you essentially take your Plasma coins and you enter this, application that is, very stateful and has a lot of participants and is, maybe a crowdfunding contract, or I don't know, whatever it might be. That contract resolves, and then you go back into a kind of like Plasma cache, state. So you don't have the mass exit vulnerability. So you don't have such a complex history, hopefully. And so this construction is more about like saying, okay, there is the possibility to build in really efficient exits. And so that opens up a class of applications that weren't really possible on Plasma before. Because one of the big questions, and it was actually asked in the Plasma contributors very recently, was like, the big problem with Plasma is generalizability. And this is really to show, in fact, we have answers for a lot of this generalizability. And this kind of approach becomes even more viable in an Ethereum 2 land where we have many shards. So this is like, just, it helps the story of, what you can do with Plasma, and not just the story, but actually the implementation, right? We will be able to implement really, stateful plaps. Coolio. I've been looking forward to, sorry?
Cool. I said cool. Yeah.
So there was one more technical thing now that we're talking about technical stuff. One of the question, Shashank, you mentioned the liveness window, I think, the online requirement.
Right.
Kind of 24 hours or a week or somewhere in between, a couple minutes, and not having good kind of intuitions about like why we're coming up with these numbers. And to be honest, I don't have the greatest intuitions either. There in the Rollup Plasma case, there is a kind of weird security constraint with the timeout window for the Rollup Plasma. But for general plasma stuff, it is a very open question. And in fact, I mean, does anyone feel like they have a good sense of why we choose the dispute period that we do?
I have a couple heuristics.
Okay.
So as far as exit windows, I think there's like two heuristics that I think are like relevant for exit windows. So I think they correspond to two cases. So one case is the case in which we have an incentivized watchtower system, and one is the case in which we do not. So basically, like, it seems, at least in the channel world, and I think I think some of the MVP implementations, maybe even OMG, have validators, what they call validators, or like these watchtowers now. So in the payment channel world, and I think we'll see this in the Plasma world, there's like watchtowers that you pay to do exit, to play the exit game for you and keep your coins secure. And so those assumptions in the channel world are like that they're always online and that they're always there to get in a transaction to the main chain, and you have some recourse if they don't. So to me, that is a world in which exit times can be much shorter. So to me, it seems I have no idea what that number is. I think we could probably look to the channels people to see what they're doing. But I think like the base intuition that I would have is that the shorter the exit window, like somehow there's going to be some multiplier effect between the exit window and the like safe amount of scaling that you can put through your Plasma chain. Because if the exit window is only one block, then if the operator in one block puts in, or convinces a miner to put in a bunch of exits or something, and you only have one block to respond to that, then it's going to be really hard for everyone to get in their exits. And you kind of can't pump more things through this chain, even though it's off chain safely, then you can process disputes on exits for. To me, I doubt that number would be as big as a week. I don't really know. And it probably depends on a lot of things like network congestion and all that stuff. But to me, there's probably like some formula to be found there that is a function of like how many exits we can fit in the block. And then yeah, sorry, this is a little long-winded, but the only other thing I would say is that there's another class of problems, which is or like this other heuristic, which is like at least the one for now that I think we're living in, especially within the Plasma Cash world, where it's practical to be your own light client and to guard particularly your funds. It's just a matter of like a UX thing, right? Because like we have this online assumption that users come online once per exit period, and if we check our phones a lot in the modern age, but presumably we want someone to be able to go on a 10-hour plane flight and come back and have a lot of time to arrive and then maybe go on their phone in a couple days or whatever. So to me, like those are the two heuristics. One is like a hard scalability limit of how much is it safe to pump through, but I'm not sure exactly what that formula is. And then the other one is just like UX. Like if people are guarding things themselves, they need time to, be humans.
Yeah, good points. Actually, both valid points. And this is also something, at least I'm going to throw in a little bit more color here, and then would love to hear others as well, is both logically make sense, right? One is the whole idea of watchtower, of somebody being live, at least one person, let's put it that way, right? At least one person being live at all times. And of course, there are boundaries both in terms of throughput or the amount of transactions you can pack in and logically sort of dispute and validate within that window. And the second one is also the UX inconvenience, right? Like what happens if I'm offline for some time, which is how when systems become more and more broadly used and adopted, you wouldn't expect people to be online, right, to save their funds. I think the part that I struggle with in this, and this is something I would love to hear, and I don't know if there is any research or science behind it or some game theory behind it or something, is what window, firstly, is a window generally, and I don't know if there is some precedent from other areas of just social behavior that is long enough to identify an anomaly, if you may, right? Because that's what we try to find out. If it's all normal, then it's all good. But some anomaly of some form, whether it's deliberate fraud or something, mistake or something, right? And so, what window is the right window? Which shows that, hey, in so much time, you can always find out in every situation, or given so many participants, it can always emerge, right? That's one part. And then the second part is, can a model be conceived where we can still have validation and convincing validation without there being a need for a watchtower at all? So the channel piece also assumes that you'll need a watchtower, but just realistically think about it. As we have more and more chains, more and more of these Plasma layer 2 pieces, we're really expecting a lot of watchtowers to work 24/7, right? Like around the clock, which is good, and which is good and optimistic. I don't know if it's realistic, right? So what if system goes down for 5 minutes? Is that somebody will just go steal everything and run away in that 5 minutes? What's going to happen, right? System. So just my thoughts, just adding more color, not giving answers. But I would love to hear, what I'm sure everyone's thinking about these, because it's sort of the key to keeping the chain safe at some level.
Just a side note to add on the Watchtower things, because I think Watchtower mostly comes with the Plasma MVP, and sadly MVP has the mass exit issue. So actually it needs longer time, because like you need like that you have like how many UTXOs actually you can put on the Plasma itself is actually bonded by the time. So yeah, that's a sad fact, but that's.
So I just had one small thought in the Watchtower line of thought. So I think the window that we decide for finalizing an exit is something like whenever each user on the Plasma chain would be able to validate the chain. So even in the case if only one user was like played around with, and if they log in into their wallet, let's say once in like whatever X number of days, so like that is a time period that we need. Okay, 7 days is something probably every user will open their wallet at least once. I think we could reduce this by having another, like a watchtower, but also incentivize to notify a particular user that you are being cheated on. So something like a CDP tracker, where you get a notification saying, hey, your CDP is going to be liquidated. So something like that, hey, you are being played around with, so start an exit. Maybe we could use that to like reduce that 7-day period.
I'm done.
So,
Go.
sorry, go ahead.
No.
Yeah. So I know actually people are actually working on it 2.0 and 1.5, 1.x, right? What will happen when you have like running mainnet Plasma chain and you need to move your coins from Ethereum 1.0 to 2.0? How it's gonna go in production?
Ooh, that's a good question. And in fact, it kind of relies a lot on Ethereum phase 2, Ethereum 2 phase 2. And phase 2 is essentially, the execution environments that will be running on top of Ethereum. So because that is not finalized, I cannot give you a finalized answer. However, there are definite general ideas. Like for instance, we may end up taking the Ethereum main chain as it is and kind of forking it into a shard chain. And then it may even become the best for us in terms of Plasma researchers, in terms of not having to do a lot of work, is we just they fork the Ethereum main chain into one of these shards, and then they give us access to all of the other shards for data availability proofs. And then we can just say, hey, let's use this, Rollup Plasma or ZK rollups or any number of things, and just pump data into these shards and maybe use them for disputes. So hopefully we don't even need to really have this long migration process, and definitely no horrible rewriting your smart contract in WebAssembly. That would suck.
That's cool then.
All theory though.
As a counter, it would be pretty cool to be able to write a Plasma execution environment that it was like a shard that all it did was deal in Plasma exit game logic. That would be fun. I would be down with that.
Yeah.
Cool. Well, we're running pretty close to the end. I did include on this schedule plip and standards. So Georgios is not here, which is very sad. But Georgios said that post about creating, some kind of place where we can post different Plasma improvement proposals. And we've, of course, settled on the word plip because it's a terrible word, like all of the other ones. But we made a repo for this. I don't know exactly what people want to do with the repo, or like what exactly it will happen with this, and how we can actually standardize. I can throw a kind of straw man out there where, like, if we have a somewhat standard deposit contract logic, then the API, then all of our predicates can at least plug into the same, can kind of be shared across a number of our, deposit contracts and therefore Plasma chains. That's probably a very reasonable thing. And so maybe one of the first plips would be an API for a deposit contract or something like this. I don't know, just throwing it out there, and I'm curious what y'all think. We only have a couple minutes, so maybe some quick thoughts. We can talk about this more next time.
I mean, we actually using the same interface as you guys are using as Plasma group for predicates. So maybe we can do something like general predicates interface in the repository. Yeah.
Cool. Well, I like uncontroversial interoperation and standardization. That's great. That's my favorite kind. Oh my god. Okay. Anyway, so any thoughts? Last thoughts, either on standards, which I'm sure we'll talk about more next time, or anything else y'all wanna discuss?
Oh yeah, I have a third one. So I think Ben talked about like the stat channel on Plasma. I'm just curious, what are the main use case for this construction?
For what?
Stat channels on top of Plasma.
Yeah. What was the question? What are the applications?
Yeah. What are the use case?
So I mean, there's a few things. Like, one is that state channels give you instant finality or instant safety without some sort of notion of trusting the operator. Like in Plasma, we already have this where we can pretty easily show on the UI that the transaction has been done because the operator promises to, and like we trust him. It's like $1, and what's he gonna do? But state channels allow you to do that better. I think generally it's just like these things scale are like a very, very well coupled scaling solution, right? Because one of the strongest problems that we have in state channels is that you have to rebalance, right? As people run out of money in the channel and want to keep sending money, they've got to go on chain. And the more money you lock up, the less often you have to rebalance. So the sort of more scalable it is, but then you have more money locked up, and so fees are going to be more expensive. So like it just seems like a great merging of the two, where if you have a Plasma chain where all of the transactions in the Plasma blocks are nothing but rebalances, nothing but updates to the balances of payment channels, and then all the actual payments are happening on this like another layer below, then it just seems like a glorious amount of play.
Got it.
Yeah. So that's channels.
Cool. Thanks.
I am worried that we're going to scale blockchains too soon, and that people will realize the blockchains have more problems rather than just scaling, because it feels like we've got a lot of headway in the scaling side, but
that'd be a great problem.
That's a great problem to have, I guess. Yeah.
That's well said. Yeah.
All right. Well, unless there's anything else, thank you all for joining. That was a lot of fun. All right, see ya.
Bye, guys. Oh, I just
Thanks. Bye.
Bye, guys. Thank you.
Thanks for facilitating.
Of course.
Take care, guys.
Yeah. Bye.
See ya.